Guys, my name is Matthew. So today I'm bringing you pharmacokinetics, which basically describes the movement of a drug around the body. So as you can see here, pharmacokinetics describes the movement of a drug around the body. Now, this is a key thing that you want to be looking at here is, so initially when a dose of drug is administered, this then goes from here into your systemic circulation. From your systemic circulation, it can then go into the drugs in your tissues as well as being excreted. Now, the dose at the site of action. So, bioavailability is something that we look at as a parameter of pharmacokinetics. If I was to write this out, pharmacokinetics, I spelled pharmacokinetics wrong, contains bioavailability. It contains volume of distribution, clearance, and it's made up of volume of VD, volume of distribution. Now, all of this combined then goes on to produce what's known as a pharmacological effect. Pharmacological effect, which is basically what we're interested in, because whatever comes out of all of this, which is known as pharmacological effect, is the effect the drug has on the body. Now we have two terms written on the bottom here: pharmacokinetics and pharmacodynamics. Pharmacokinetic is what the body does to the drug, whereas pharmacodynamics is what the drug is doing to the body. So two different things, and we're concentrating on pharmacokinetics here. So what the body is doing to the drug. Now, so what we want is bioavailability. The definition, so here it's written as the fraction of unchanged drug that reaches systemic circulation post-administration. So bioavailability, so if I was to get rid of this, bioavailability. So if we have a drug capsule of 20 milligrams, once we administrate it, the bioavailability is the fraction that so here's our blood vessel. So bioavailability is how much of this drug reaches the systemic circulation, and usually a very low amount. So this could be somewhere between 1 and 5 milligrams, and the rest is what you call is excreted. So the rest is excretion. Some is bound to plasma protein. Some is bound to the tissues. So adipose tissue is example. You got plasma tissue. And what I'm going to do here is I'm going to put these ones in green. These green dots here, these are drugs that's bound to plasma protein. Like albumin. Example of plasma proteins include albumin, P-glycoprotein, and various other ones. So that's bioavailability. So the bioavailability looks at how much, so this is what we initially dose, and this is how much gets into the systemic circulation. Right now, clearance is something a bit different. Clearance is the volume of plasma or blood from which drug is removed per unit time. Right, so you know clearance can happen through sweat, breath, urine, various different ones, and we'll go into considerable detail as we move along these lecture. Now, volume of distribution is the apparent volume in which drug is distributed. So it relates the amount of drug. So if I was to write that out, VD is equal amount in body divided by the amount in blood. Right, so this basically shows the distribution, the apparent volume of the drug that is distributed. So the amount of drug inside the body divided by the amount in the blood. Okay, and VD is usually done by dose. So dose is like the initial how much we administrate. So if we were to administrate a 20 milligram capsule, then you have 20 milligrams of that drug inside your body, and then what we do is C0, which is initial concentration. This is the amount that's in the blood, and this is how we work this out. Now, common examples are amoxicillin, which is an antibiotic, theophylline, which is chronic airway, so respiratory disease, ethandiasterol, ethanol, lestradiolol. It's an oral contraceptive, usually taken once a day. Right? Chloroquine is an antimalarial drug. Mefloquine is also antimalarial. So, skipping through all of this, what we want to now look at is something known as drug administration. Right? Drug administration is shown here. Now, as you can see here, half-life is the time taken for drug concentration decline by half, and K is the rate constant of elimination. Right, so the equation that links half-life and K is equal to 0.693 divided by half-life. This is the equation that we use. So half-life is the time taken for the drug concentration to reduce by itself. So if a drug concentration, in this case, so let me give an example. So if an initial dosage was 20 micrograms, and the plasma concentration, which is what we're interested in, so initial plasma concentration at T is equal to 0 was 12 microgram, then half-life would be the time taken in order for this, so whatever is time in hours or in minutes, is mostly in hours, most of these drugs. Make sure you put units, it can be minutes, hours, some drugs can be days, some can even be in months. Alright, so it will be the time taken for it to become 6 micrograms, so half of it. So that's what half-life is. So in this case, you have a concentration here. The initial one is 100. Let's just pretend that's 100, even though it isn't. Half-life of that will be 50, somewhere here. And you read across. Now, another key equation that we use is the rate of decay equation, which is plasma concentration is equal to the initial concentration times e to the minus kt. Right, T is the half-life, K is the rate constant of elimination, E is a standard value. You just plug it into your calculator. C naught is the initial, and this is plasma concentration. So we've gone through this. Apparent volume of distribution, it's the amount in body divided by the concentration. If a drug is avidly bound in tissues, the concentration in plasma will be low. So therefore, if a drug is avidly bound in tissues, it basically means the VD will be low because the VD will be high. Sorry, it's because there's loads in the amount in the body, but the concentration in the blood is really low. So you have a bigger number on top divided by a smaller number, which means you end up getting a bigger VD value, volume of distribution. So these are examples of calculations. So imagine this is the blood. So we have an initial dose of 20 milligrams. The initial concentration is 0.5 milligrams per liter in the blood. So drug A would then, the volume of distribution would then be 20 divided by 0.5, which is 40. Similarly, again, 20 milligram administered and 4 milligram per liter, 5 liters, and so on and so on. So an average person with a body weight of 70, right, would usually have about 40 liters of water within themselves, right? Now we know the human body is about 75% water, right? The intracellular water is 25, blood is 5, plasma is 3, and extracellular water is 15. Right, so these are common values and an average of a 70 kilogram patient, or a human, you could say. It doesn't have to be a patient. Alright, so the amount of blood that's circulating around at a given time would usually be around 5 liters. Now this can increase depending on your the amount of blood in circulation can increase. So there might be at any given time, or in a minute, it will be more than 5 liters when you're doing strenuous exercise, because obviously you need to get more oxygen and glucose and everything into those respiring tissues. Alright, so now over here we have the key binding proteins. So these are plasma proteins, so these include plasma albumin, CBG, which is corticosteroid binding globulin, sex hormone binding globulin, which is HBG, and finally you have alpha-1 acid glycoprotein. But the main one that we're interested in is albumin. This is the most abundant type of plasma protein within the plasma. Now on the right you can see different types of drugs. So chloroquine is an anti-malarial. Digoxin is used to treat arrhythmias and heart failures. Propranolol is also something, a drug used usually to treat arrhythmias and heart problems. Tetracycline is an antibiotic. Warfarin, which is an anticoagulant, and theophylline, I can't remember at the top of my head, but I believe theophylline is used in, not exactly sure, so if you want to search it up, and then I did know it, but I just forgot it. If you know it, please leave a comment below, or I'll try to remember it by the end of this video. So the basic what we're looking at over here, it's the chloroquine has a volume of distribution about above 10,000. So this means, what this means is, so if I get rid of that, so you know initially VD is equal to amount in body divided by plasma or blood concentration. Now if you have a VD of, like chloroquine has a VD of around 10,000, alright, so a VD of 10,000 basically means for every 1 milligram of chloroquine, or basically means the amount in the body, it's 10,000 more compared to the plasma concentration. That's a very simple way of putting it. Digoxin is around 800, propranolol 200, tetracycline 100, warfarin is around 8. Okay, so now clearance is a very important thing. So this is how we remove the drug from our blood, right? So clearance can be measured in 2 ways. So clearance, the first definition is the volume of plasma from which drug is removed per unit time. Right, now pay close attention to the per unit time, because that's what most of the units of this equation are, right? And depending on the rest of the numbers or the values given in the question, you can then determine what per unit time is. Is it per minute, or is it per an hour, per second, and so on and so on. Right, now, so clearance can be determined by rate of elimination by concentration, and this is usually rate of elimination is given in milligrams per minute, and concentration is given in milligrams per mil. So when you cancel these two out, you end up getting mil per minute. So that's rate of elimination. Or another equation will be plasma total plasma clearance, CLP, is equal to volume of distribution, so the amount of drug that's in the body compared to plasma, times by the rate constant of elimination, right? So this can then be simplified into CL. So there's a total plasma concentration is equal to VD times, so you know K is 0.693 divided by K, which is the half-life. There's another way of writing the equation. Now, for example, if you were to be given a graph and you were told to work out the rate of elimination or the clearance, then you could first, what you do is find the area under the graph, which is done by the initial concentration, right, and then you divide it by the rate constant of elimination. So initial is like how much you had initially, and how much is going down. So this gives you the area under the curve, and then clearance can then be figured out using dose divided by area under curve. That will also give you clearance. Now, an example question to attempt to see our understanding would be, So a dose of 50 milligrams of drug A is given by intravenous administration, and the following plasma concentration time relationship is determined. Right, so this is the equation that's given to us. So C is equal to 1.2 0.173 T, where C is expressed in micrograms per milliliters and T is in hours. So pay great attention to that. Now the first one is calculate the half-life. So saying calculate the half-life. So you know half-life from the equation, you know half-life is equal to 0.693 divided by K. Right, so you can easily do this as 0.693 divided by 0.173. So we ignore the negative sign. So 0.693 divided by 0.173 gives us 4 hours. So the half-life is 4 hours. Now, question 2 asks the apparent volume of distribution. Right, and you know volume of distribution is VD is equal to dose divided by initial. So initial concentration can be figured out, so you can plug it into this equation here. And so initially when time is 0, so this is the initial concentration 1.2. So what you would do is simply 50 milligrams divided by 1.2 micrograms per milliliter. So now we need to be a bit careful here, because this is given in micrograms and this is in milligrams. Right, so to get from micrograms to milligrams, you simply times it by 1,000. Right, so what you do is a milliliter times by 1,000 would become liter. So this can be easily written as 50 divided by 1.2 milligrams per liter, which would then give 50 divided by 1.2 is 41.6666 recurring 7, so you write 41.7 liters. Makes sense? Because the mg and the mg cancels out, so you're just left with the liters. Right, now if we get rid of all of this, so it's asking for the area under the curve now. So the area under the curve, so AUC was defined as initial concentration divided by K. So this would simply be 1.2 divided by 0.173 is equal to 6.94. So 6.94, the concentration is given in micrograms per milliliter, so micrograms per milliliter, or you can change it as milligrams per liter, right, whichever you want. And question 4 is clearance of A. You know clearance is Vd times by K, or you can do dose divided by or dose divided by area under curve. Now if we were to do both of them, well, we should get the same answer. Right, so the volume of distribution I forgot the value, but anyway, I'll figure it out. So volume of distribution was 50 divided by 1.2. Yeah, that was 41 point something. Now you times that by K, which is 0.173. So you should get a clearance of 7.2 liters per hour, or and if you were to do it this way, so dose, which is 50 milligrams divided by 6.94 milligrams per liter, because I converted the micrograms into milligrams. So milligrams is obviously bigger than micrograms. Again, you get the same value of 7.2 liters per hour. Okay, so there you go. That's how you work these questions out. Now, I've got another question here. So, calculate the half-life of a drug in a subject in which the clearance and the volume of distribution are 125 ml per minute and 80 liters. So Vd is given as 80 and clearance is given as 125 mils per minute. So now the first thing that you want to look out for is the units. Here is in liters and here is in milliliters. So what you need to either convert this one into milliliters, or you want to convert this one into liters. Now if there's 125 milliliters per minute, this is the same as saying there is 0.125 liters per minute. Right, so in an hour, so in 1 hour, there will be 0.125 times 60, which is 7.5 liters per hour. This is the clearance. Now you know clearance is equal to Vd times K. Right, so you can do 7.5 equals 80 times K. So K is equal to 10.6 recurring. Right, now the units of K would be liters divided by liters per hour. So it would be units of K would be liters per hour divided by, this one was litres, over 1, so it would just be per hour. Now what you can do is half-life, it's 0.693, this is a naught, divided by 10.6 recurring. So half-life is equal to 0.64 hours, or if you want to convert it into minutes, you times by 60 will give you around 4 minutes. Oh, I think I've done something wrong here. No, this bit is wrong. Sorry, I did this bit of the calculation wrong. It's in fact meant to be 7.5 divided by 80. Now this whole divided by 0.693 will give you t half, which is equal to 7.4. Okay. Hours. Gonna put that in. Right. Hope that helps. Now let's move on to the next one. Patient on digoxin develops toxicity. The plasma digoxin concentration is 8 nanograms per ml. The plasma half-life of digoxin in the patient is 1.5 days. How long should they wait in order to get to 1? So this is simple. What you can do is 1.5. So no. So when time is time concentration, so when it's 0, so when the patient is first admitted, so this is measured in nanograms per ml. This was a concentration. Now when it's 1.5 days later, it'll be half of this, and 3 days later it'll be half of this, and another 1.5 days will be 1. So the answer is 4.5 days. So there you go, that's how you work out volume of distribution and half-life and everything. The next video I'll be concentrating more on clearance and things. If you have any confusion, please drop a comment below. And it's a new channel, so I'm like doing this for the first time. By the way, all this lecture slides here is taken from the University of Liverpool, so by no means are these lectures created by me. So all credit goes to Dr. Geoff Edwards of the University of Liverpool. I'm just using this as a template, so all credits and all rights go to the university. But yeah, thank you for tuning in, and please leave a subscribe and leave a comment if you didn't understand anything. I'm more than happy to help you out. Thank you.